But like I was saying, thanks for coming to the open source caching engine powered by cache acceleration software, or also known as OpenCAS. My name is Jay Guilmart. I'm the Intel product marketing engineer for Intel CAS, as well as Intel Virtual RAID on CPU, or Intel VROC.
And I'm Tomasz Zowadski. I'm cloud software engineer at Intel, and most importantly, SPDK developer.
And today we're here to talk about a very exciting new development in the caching software space. Previously, Intel had developed the Intel Cache Acceleration software as a proprietary product that we sold into the market. But there's a very big change that it's been out for a couple quarters now, but we're really focusing on bringing it to the community. And this is kind of our first event where we've been able to engage with developers and really talk about this new change where we're transitioning to an open CAS or an open source model with this software. So we want to take the next 45 minutes or so to talk about what that means for the product, how it differs from the initial Intel CAS proprietary software, and start to discuss how developers and people in the community can take advantage of this new software package and start to use it in a way that really accelerates their hardware. So we'll talk about what is CAS, because the Open CAS or the Open CAS framework is based on Intel CAS. We'll start by talking about what that initial product is. Then we'll do a brief introduction to OpenCAS, which is the new open source version. Tomasz will go through a quick overview of an OpenCAS SPDK integration. So we're our own code base that's a caching engine, but we integrate into other applications. So SPDK is one of the first applications that we've built an adapter for, and so we're going to talk about as an example of how it can be used in different situations. And then we'll talk about the different resources that are available for OpenCAS. It's already posted to GitHub, and we have a lot of documentation available for the community and for the developers to start working with this software. So first, what is cache acceleration software? Because this is really the code base that OpenCAS is based off of, we want to talk about what that product is. So first, Intel CAS versus OpenCAS. They have very similar names. What's the difference? But I don't want you to think about it as one versus the other, but rather a transformation going from Intel CAS to OCF. So Intel Cache Acceleration software, like I said, was Intel proprietary. It was put into use through kernel patches and QEMU patches, and it was really enterprise supported by Intel. But it had a limited reach, right? We could only do so much with that software, and we really felt that it had a really great caching engine, some unique differentiation advantages that we wanted to allow more people to use and really give more people a better tool to leverage Optane storage technology to accelerate a variety of different applications. So the last release of Intel CAS was 3.8. We took that exact code base and brought it to the open source, and that is OpenCAS. So one of the big differences is it's open source, but rather than being a patch, it's really just a library. So that caching library is what's called CAS Framework. So OpenCAS is the product, and then the library for the caching engine within that project is the CAS Framework, or OCF. So you'll see that OCF acronym used quite a bit throughout this presentation and a lot of our documentations. So we're moving it to be kind of a library that can be plugged in to a lot of different use cases like SPDK or QEMU. And really now being fully supported by the community. Trying to get developers involved, just like SPDK, who's been at this a little longer than us, right? We're just a quarter in. We want to generate a similar community atmosphere. So people are looking at this code base, they're looking at unique ways to use this caching engine, and coming up with different adapters and ways to tie it into their applications so they can see an actual business benefit. So just talking about how does this caching engine work? What does it actually do, right? So it's a block caching storage software. So this is your very typical storage subsystem where you have two different types of devices that you classify within CAS. You have your caching devices, which is where you put a lot of your hot data, often metadata or things like that are written frequently and that you're trying to accelerate the performance. And that's going to be your fast front-end storage, right? You want your cache to be quick. You want it to be hot. You want it to be able to move the data quickly and accelerate some slower media in the back. So very frequently, this is a TLC or an MLC SSD, an NVMe SSD, or it's really designed heavily for Intel Optane devices, giving you that big performance boost without necessarily needing to buy a complete Optane storage array, right? You can have a small piece of Optane accelerating a high-capacity back-end storage. So you put some of your slower, more cost-effective devices as the core devices. That's what we call the back-end, cooler storage. And that'll typically be the newer QLC SSDs that have a little bit better price point, but are also a little bit slower, or even HDDs. We have a lot of use cases of customers having an existing storage infrastructure with a lot of hard disk drives and just dropping in a caching device that's either an NVMe SSD or an Optane device and seeing a lot of storage improvement. So Intel CAS is just the coordinator that helps specify which IOs are being sent to the cache device. We have a bunch of different modes, like write through, write back, write around. And so you set it up, configure it in different ways to make sure that your cache is best utilized and giving you the most storage improvement on your application. So just kind of listing through some of the unique benefits and features that come with CAS. And again, just really focusing on the CAS version for now, because this is exactly what OCF does, right? It's easier to talk about something that's existing rather than focusing on a newer product. So everything you're seeing here is then translated down to OCF. So one of the biggest advantages that Intel CAS has is smarter caching with I/O classification. So there's a tool within the CAS code that allows you to trace your different I/O classifications and see what different block sizes are coming through. And you're allowed to use that for different hinting policies to say, this types of I/O I want to send to my caching device. And that way you can kind of signify what types of block sizes are metadata or logging or anything else that you've identified you want to cache, and you can directly send that to the caching device in an intelligent way. And that's really how you get that kind of tuned performance that's perfect for your workload. And that brings you to the second point. That really delivers the incredible performance. You may have saw in the keynote talk earlier that in many use cases like Ceph, we get up to 5 times performance improvement. And we'll go through some of those performance numbers for different applications in a little bit, but really great performance increases. It is optimized for Intel Optane SSDs. Not necessarily focusing on Intel there, but focusing on the very fast Optane devices. You want your cache to be extremely fast, and Optane is some of the fastest storage on the market. And just going through some of the others, really some of the examples of where it's used is application acceleration, virtualization, and software-defined storage acceleration. So again, it's a very flexible product. If you can just think of it as a basic caching engine that can then be plugged into a lot of different other sources. And so if you want any information about the Intel version, it's at intel.com/CAS, but a lot of the information is now available on the OCF websites as well, which will give everybody that information here soon. So this just expands on that performance improvements that we've seen when implementing Intel CAS as the caching software. So for application acceleration, we have worked with a lot of different companies to figure out what are their specific workloads and how do we really boost their productivity, right? We give them a solution that allows them to do something quicker or reduce the amount of time it takes to complete a task, and that directly correlates to business value, right? So it could be a standard application like a MySQL workload, but we've even worked with some custom applications. If you see the one in the middle with oil search, they were using a proprietary analytical software to understand where different oil patches were. It took in a lot of data. It took several days to work through this data and come out with an output that they then used to make business decisions. By putting certain data on a caching device, they were able to decrease the amount of time to do that software run by 5 times. So it went from days to hours. So that's direct return for a company that makes money based off of providing insights to their customers of where to drill for oil, right? We got to do anything to make sure the oil keep making money, right? We don't want to, they're struggling right now. So you can see how it's very application specific, and we can plug into any of those unique applications. Going down to the next one, virtualization, virtual machine acceleration. We work with Aliun to get 6.1 times the virtual machine performance. And again, this translates into direct business value for Aliun. They're able to sell better service level agreements. They're able to provide a better service to their customer, have better customer retention, less problems, things like that, where they can directly see how their infrastructure, their storage infrastructure, and their IT development is directly impacting the bottom line and helping drive more revenue. And then cloud storage acceleration. We have a lot of use cases with Ceph or SwiftStack, where again, by adding a Optane SSD as a caching device in front of your backend storage, can have almost 5 times or 3 times performance. And again, in some cases, this is just by adding the cache. You can take your already existing hardware structure that you're storing your clusters on and just add the cache to that already in place infrastructure. So it kind of is a good way to bridge the gap until maybe you're waiting to upgrade for a year or two, but you need some performance relief now. This is a great way to add CAS to your storage stack, plug in just a single or a couple SSDs, and provide that for a cache for your already slow backend storage. Yeah.
I'm new to this cache product. Some time ago, Intel have IMD,
Mm-hmm.
the memory drive technology. I think the consumer implementation is Optane memory drive or something. Right?
Yeah.
Are those a part of this, or are these completely separate?
They're kind of completely separate. This focuses more on just caching data and more in the block space. IMDT focuses more, I think, on allocating the Optane space as kind of a memory swapping area. So it's kind of two different aspects. So you consider those both as different tools to accelerate performance, but that's a little bit different. Yeah. And yeah, feel free to ask questions while we're going through this. And then just to talk about one more kind of in-depth approach on how we use this caching software to break through storage bottlenecks, right? There's a lot of applications out there, people using Hadoop clusters to do a lot of analytical computation. But as the workload increases and you need to add more storage, very frequently people are adding more and bigger hard drives in order to store all that information. But when you're storing that on hard drives, that directly correlates to slower performance. It's longer seek times as the drive gets bigger, and that can impact your ability to run these Hadoop processes quicker. So what we did is we analyzed the workload and said, what data can we shift onto an Optane caching device in order to make sure this runs quicker? And so what we did is we directed the yarn data, which is yet another resource negotiator, which is the resource manager for Hadoop, and said all of that data should go onto this specific NVMe SSD, right? So the backend storage was all HDD, which was too slow, and it was getting slower as more capacity was added. We took the yarn data, directed it to just the NVMe device, and we got a 2x performance increase. And one of the big advantages that CAS has, or this caching software has, is it allows you to smoothly manage heavy data traffic. Because theoretically, even without a caching engine, you could direct that yarn data to a different storage target anyway. But what the caching software actually does is it manages in heavy workload so that if that yarn data was going to overpower that SSD, you didn't have a lot of issues with that heavy traffic causing bottlenecks back to your backend storage. So caching actually allows you to smartly manage that yarn data and prevent any performance degradation or too much performance degradation during heavy traffic. So this is just another way where we plug in the software into an already existing workload to see a pretty substantial performance increase. So that was Intel CAS. So everything I just said, replace Intel CAS with OCF, and it still exists, right? We just wanted to get everybody familiar with what the solution is that we're talking about. So what we did for OCF and the OpenCAS project is we took that code base, like I said, last quarter, or 2 quarters ago now, in December of 2018, and took Intel CAS 3.8 and moved it to the open source, right? So we have our GitHub repository already loaded up, but that initial drop didn't have a lot of functional use, right? Like I mentioned before, while Intel CAS was a kernel patch that could be dropped in and immediately used, the OCF is just a library within this project that needs to be implemented into a variety of different applications. So we launched the library last year, but then the first quarter of this year, we added our first couple adapters, right? So we have a Linux kernel adapter and an SPDK adapter so that this caching engine can be rolled into the SPDK and the Linux kernel, allowing people to actually use the caching engine for a variety of different use cases. So moving forward, we have a lot of good things coming to the roadmap, but we really want to, yes?
So I would like to know what does adapter exactly do in the framework?
Yeah. Hey, Tomasz, you want to take this?
So the adapters themselves, so OCF implements the logic behind the caching. Meanwhile, adapters are the ones that actually interact with the devices from both sides, from the top when the I/O is coming, as well as to what devices it's written. For SPDK, I'll actually go through the whole integration, how you can do similar thing with your application or just use SPDK. So later on, I'll get to that.
But part of the key is, right, is you need that level of that adapter to do certain functions in order to integrate the caching into a specific application. And like Tomasz said, we'll show one instance of that. But as we go forward with the roadmap, we have some ideas of what Intel will be adding to this community, but we're now looking to the developers who will hopefully be taking this caching engine and looking for new places to integrate it to help come up with new adapters and new features that we should be adding to this, right? This is based off of basically what we had left over from our Intel CAS roadmap, but now that we're open source, it's really about driving this roadmap forward with the community. So a couple of the main things I want to point out is, at first in this quarter, in June, we're coming out with our 19.06 release, which will include a kernel I/O tracing capability. And so what we're working on is some storage analytical tools that allow people to exactly see what their workload looks like, kind of like similar to what vTune does in a certain way. But the way we analyze that data is we take a log from what that I/O tracer puts out and then provide feedback to exactly how your cache should be optimized. So there's certain configurations like cache line size that need to be set up in the proper way based off of your workload. So we're coming out with a tracer that will give users the ability to see what their workload is exactly doing at the cache level and then optimize their cache process to make sure that it's the perfect setup for their data. And then
Historically, one might do something like that with block trace, block parse, or something. They have a horrible performance impact. How's this thing going?
you're talking from the tracing perspective, right? So we're trying to make it as lightweight as possible, but the real way it's going to work is it's not something that's going to be tracing, at least not now, continually, right? So you'll run it for a couple hours or a day, and then take that log information and actually run that through the analyzer that we're putting together in order to give you the proper feedback on how things should be tuned. So while we're trying to make it as lightweight as possible, because it's not a continued thing, I'm not sure what the performance degradation will be, but I'm not sure that we're overly focused on it making it, you know what I mean? Okay. Oh, that's fair. And I will say that over time, right, if you looked at the long-term concept that we're looking at for this tracing capability is to have something that you would leave in place. And that way, as the workload shifts, or even if over a period of a week, maybe you have different workloads on different days, and it can begin to learn those different nuances of your workload. So this is kind of the first release that we're coming out with, but I would say over time, we definitely want something that's more leave in place. So just to talk a little bit more about what does this open CAS project actually look like. So if you go to our GitHub site right now, you'll see a couple of different code bases that you can pull from, right? So the open CAS framework, like I mentioned, that's really just the caching engine. That's the library that you can take and adapt into other software. But then we need these adapters to come in and actually allow you to utilize them in different instances. So the SPDK adapter and the Linux adapter are already there, and then the QEMU adapter should be coming out roughly next quarter. But again, I want to really emphasize the fact that we want to come up with other adapters, right? We want the community to help generate new ideas of where this caching engine can be implemented so we can grow this web into many, many more nodes of different applications and adapters that are really utilizing this caching software. So our release plans, as we go through the year and people are contributing to our code base, we kind of have this quarterly flow of when we'll pull the code that's out there, validate it at a standard validation level, and come out with kind of validated packages every quarter. So there'll be, at the code check-in, we do kind of our focused validation to make sure it compiles and is kind of custom to whatever the patch is that's going in. And then every quarter we'll do a standard validation to make sure that there's a code base that people can follow. And if you need to pull that and put into a production environment, those are going to be the kind of releases that you're going to want to pull from to make sure that it's stable and of high quality. But because it's, this isn't necessarily a new product, right? We've had 5+ years of Intel CAS already behind the code base that's existing on this repository. So it's already very stable. So we're confident that the ability for it to be production quality immediately is very high. That's a good question. It technically still exists at a name, and maybe mainly because we want to make sure that we're available for certain support agreements, right? People may have the ability to pull this code base and use it as is, but we're not necessarily innovating on our own separate product anymore, right? We're focusing all of our effort into this OCF, and really Intel CAS is just pulling the OCF and having a enterprise validated version that could be supported for a customer if that's what they needed. So we are available for that level of support. And that brings up a good question is why are we doing this, right? Why are we going from Intel CAS, which has been an existing product for several years, to the Open CAS Framework or Open CAS? And it really has to do with accessibility, right? We think there's a lot of value in engaging with the community and getting people more access to this great caching engine, right? We want people to have high-performance products that really are ready to integrate into any type of software, and that way they can pull different types of storage devices like Intel Optane and accelerate that into their workload. We also see a lot of value of focusing the collective power into one innovation train, right? Our team at Intel, we were innovating on this one code base, but that's not even going to compare to the innovation that we can generate when we have a lot more eyes out in the world looking at how to use caching more effectively and driving innovation cycle on one specific code base. And then finally, adding to all that, it's just about creating this transparent community that we've seen be so successful with our SPDK and PMDK, family members at Intel, showing how they led the way to show how Intel can create this software, move it to the open source, and just become a part of a larger community, and how that can be very valuable for everybody involved. So I'll now pass it off to Tomasz, who will go into more about the OCF and SPDK integration.
Hello. So I would like to show you with this opportunity that OCF, OpenCAS, generated at the end of the last year of open sourcing the CAS software. We took this chance and became the first openly available OCF adapter. And now I will go through how we use it in SPDK, giving examples, and how possibly others could use OCF directly or through SPDK. So just to establish some basic terms, simply because the SPDK has its own set of terms, so does OCF, just so that we're on the same page later on in the presentation. First of all, there's volume. This means any kind of device that is being either cached or that is the cache itself. Sometimes it's called volume, other times bottom adapter, depending on which parts of the code you look for. Then there's core device. This is the device that is being cached. The main point of this device is that there are no data relating to caching written on it. If you were to remove all the cache altogether from your solution, the core device stays the same. Meanwhile, the other one is the cache device. It contains all the data that is being written or read from the device, as well as some additional metadata like mappings between the devices. Of course, there's cache modes. Their logic itself is complex, and there's no single solution for any kind of application that you have. The decision has to be made consciously which one you choose. Of course, there's different sets of configuration besides caching mode, which I will not go into depth, but you should look that over. So throughout the next slides, if you want to see actual implementation as an example in SPDK, on the left bottom corner, you'll see where you can find that in SPDK repository. Briefly, I'll go at first how to use OCF, and then give an example how it's done in SPDK. The green block is for SPDK, blue for OCF. Starting out, as mentioned multiple times, OCF, Open CAS Framework, is just the logic for caching. It does not contain any interaction with the actual devices. There's no NVMe driver, there's no usage of it going up from the OCF. There are no additional dependencies outside the OCF. When you've got OCF, you've got all the logic already there. You do not need to pull anything else beside it. SPDK includes OCF as a Git submodule. If you want to start using it today, just configure SPDK with option with OCF, and you've got it. The version of OCF and SPDK at the time you've got the SPDK revision is validated through our usual SPDK CI system. And upgrades are being done on each of the SPDK releases. So far we had one, but soon there will be more. OCF environment. The OCF is designed to run in any kind of environment. The adapters that were described previously are a great example of that. Either you're running in SPDK, Linux, QEMU, possibly many others. All of this makes OCF completely platform independent. So the providers of the environment need to have implementation for different set of operations. Main ones would probably memory allocation or threading model, and there are a couple of others. This suits pretty great to SPDK simply because we already have all the abstractions around things like threading and memory for ones that were specific to OCF that we needed to implement. Those are present in environment specific to OCF within the directory for the BDEV. Then, OCF interacts with the devices beneath it in transparent way. There's no way to specify from the top of the OCF library which device the I/O will go to. This is the logic that is within the OCF itself. The bottom device can be either cache or core device, as mentioned. Core devices, you would want to have the ones that are the high capacity ones, meanwhile the caching is the higher performant one. In this example, that means basically using, providing OCF framework callbacks to use BDEV APIs. This implies NVMe BDEV or any other kind of BDEV that you prefer. So then we get to using OCF framework from the top. This is done, once again, it's completely abstracted out. It is done through OCF APIs, which in SPDK's case means that we expose a new type of BDEV, OCF BDEV, that receives the BDEV API calls and translates that to OCF APIs. You would probably do the exact same thing if you were to use OCF in your application without SPDK in that solution. Altogether, that makes OCF and SPDK a great combination simply because we got all the abstractions needed for OCF. The BDEV layer, the stacking of BDEVs and virtual BDEVs make a great way to combine OCF into this solution and enables any other kind of usages that you were using previously work exactly the same, just putting OCF BDEV between the BDEVs you are using already. So SPDK 1901 was just the start of the story. Both OCF and SPDK will go further. Jay already mentioned a lot of improvements to OCF by itself, but there are still some things we are pulling from OCF and need to implement. For the 1904, we're adding multiple core devices on a single cache. At the 1901 release, it was just a single device. Using this, you can attach multiple core devices, and amount of the space that is being used on the cache device for each of those core devices is decided by the logic within OCF. This is a bit different if we were to use like LVOS just to split up the cache device. Another one is adding write-back cache mode with persistent metadata on the cache device, allowing for even other use cases. So, floor up on the demo display, you can see demo from OCF team displaying the results of their performance evaluation with SPDK and OCF. Just briefly, if you want to know more, see the guys. We are using RAID for TLC devices, comparing it to QLC with Optane running Open CAS BDEV in SPDK. The results are very compelling. We see 3.4 times performance improvement in that specific workload of 16K random reads and writes with 8Q depth. For more, as I said, please see guys up above. So OCF resources. If you would like to see what's up in OpenCAS, please go to the GitHub IO page for OpenCAS. There you can find all the documentation required to learn more. As for GitHub, there's OCF project there, which is main source repository, code source repository for it, as well as it's a place for interaction with the community. You can ask questions, file any findings that you find. And of course, it's the place where you can contribute back to the OCF community. So with this in mind, I would like to encourage you to go to the website, learn more. You can do that right now. If you want, SPDK is available today and start using it. Tomorrow, we have at 1 p.m. lab for SPDK, which will contain in part OCF configuration, how to use it, etc. We encourage visiting it tomorrow. That's
about it. I just want to add one more thing as we close up here, and then we'll take any questions. I'm not sure what time this session officially ends, but being a new open source project, kind of announcing it today to a lot of developers in the room and at the conference, we're really looking at that next level of engagement within our community. Right? We have a lot of people currently within Intel on our application engineering team who have a lot of experience with this exact code package, and we're looking to collaborate with people who are already interested about integrating OCF. So if you think this is a tool that may be advantageous to your platforms or your customers or into your use cases, please come talk about that with us upstairs as we're manning our demo or after this presentation is done, and we'd love to start engaging right now and figuring out how this can help bring value to you and your company. So thank you very much, and we'll take any questions if there are any. We got two.
So on the backend code device, when you do the writes to that, do you also handle any alignments like if the backend code in this QLC works back on 64 kilobyte block sizes, front end IO can run on 4K? Does OCF handle that also?
So the question was, how do we handle alignment when writing to backend devices? So since OCF handles a certain set of IOs, one step back. The interaction for OCF in SPDK is through BDEV APIs. Basically, anything that's available in BDEV APIs is available to OCF, meaning that we configure OCF depending on the knowledge of the BDEV we have, right? The alignment, if it's required or not, what alignment it is. And in those cases, we provide that same alignment to the top of the OCF BDEV, meaning all of this can be handled within SPDK or OCF as you've configured the BDEVs themselves.
So is it possible to configure OCF so that the OCF BDEV has a smaller block size, whereas the core BDEV has a larger block?
No, we're actually using the same block size, I think, as either core or cache device, just to, depending on what are the differences between those.
So his question, right?
Yeah.
The Optane, right, as a first cache, 4 kilobyte block, right, and then QLC P4320, right? 8 kilobyte model is a 4K, right?
It's back to the 64.
Yeah.
That's 64 or something, right? So different block size, we cannot use that.
Yeah.
So the available block sizes so far are 5 kilobytes and 4K. Bigger block sizes are not available so far. So we
devices, even though they expose 4 kilobyte to 1 byte block size, they actually work better with the larger block size. Right. So your caching device can have a much smaller block size, whereas the slower device, which you are trying to cache, have a much larger, have a preferred much larger block size. A caching layer can actually provide you.
Yeah. So in that sense, we start to optimize for QLC type of SSD, which prefer actually bigger IO sizes.
Right.
So one of the improvements that we are considering is to submit big IO sizes, like 16K of 64K. This is specific to address the challenges of QLC SSDs.
Right.
Yeah. So specific changes in new policy, flashing policy.
He's with us, by the way. That's the architect on OCF and our caching software. Yep.
So cache is obviously better or worse than hit ratio, residence time, a bunch of statistics like that.
Mm-hmm.
Do you have tools or assists to help size the cache for a given policy? Can you watch the cache in operation and understand is it big enough, for example?
Yeah, so part of the OCF library within that software package is some IO classifications, what we call it, and that's where it actually, throughout your workload, it'll track of the different types of packets that are coming through and classifies them into different bins and buckets. So you can look at that data to figure out what your workload looks like, and then look at how those specific IO classifications are hitting the cache, which ones are maybe missing, where your problem areas, so you can then begin to make intelligent decisions about how you should be optimizing your caching device. That's where we are today. It's kind of maybe a bit more manual than we'd like it to be. So tomorrow, we're focusing on that IO tracer where it will actually track all that information and provide a log that we can run through an analytical engine to come up with more direct recommendations without you having to necessarily know what all these different outputs mean. And then, a year from now or whatever, when we make some even more changes, then we start to try and automate that into more of an automated recommendation that'll say, hey, if you do this, it'll improve your caching performance by X amount. Do you want to do it? Things like that. So we have a certain degree of that today, and we're continuing to try and innovate around that to make sure that it's an easy lift to implement and get the proper performance. Mm-hmm.
Yes.
You mentioned that there's a way to provision how much of the cache device space should be provisioned supporting multiple core devices. Is that something configurable or is that?
So what I mentioned was basically you can use the tools provided in SPDK, like logical volumes, to split up the core cache device, whatever BDEF, into multiple parts. This is one way if you were to use SPDK 1901 and didn't want to use the full capacity of cache device. Meanwhile, for 1904, you still could use the whole device, but for multiple cores. That's what the improvement is.
Right, but how much of space is consumed for caching for each of the 4 devices? Is that something configurable? Oh, sorry, thank you. So what my question is, like, if when you're supporting multiple core devices and using a single cache device for caching, right? How much of space in the cache device is consumed for each of the core devices? Is that something configurable, or is that automatically determined by the caching layer?
Okay, so for this, there's no configuration in SPDK to configure OCF, but I would need to check within OCF Framework whether that's possible.
Okay, thank you.
We got one more in the back, and then we'll come back.
How much memory do you use for your metadata RAM?
Yeah, so there's definitely some overhead in the memory used in RAM when you're caching. I think we've got it described in SPDK documentation. That's a considerable portion of the memory used, but I'm not sure on the exact number right now.
Does it scale with the amount of, the capacity of the SSD, or is it like?
Yes, it scales with the capacities, definitely, yeah.
another general question. There are a lot of open source caching, right? B cache and other stuff, DM cache and other stuff. Why do you start your own? What is the logic behind that? Why can't you, enhance the existing ones, right?
Yeah, there was some, we did some review of, and actually I think it may be in here. I thought I put it in here. Oh, maybe not. I thought there was a slide in here that talked about it. Those caching software didn't have at least today, didn't have a lot of use cases and community driven around it. So there wasn't a lot of usage and innovation around that. So there wasn't, it wasn't really a good enough product. We thought we could do something better that better utilizes the new hardware available from Intel, like Intel Optane. So we just felt that there were some gaps in what it was providing. I don't know, Andre, do you have any specific?
That's exactly the reason. So we strive to optimize, for Intel hardware, specifically Intel Optane SSD and NAND type of SSD. And working, for Intel positions are better because we know, better how to place the data and how to make the combinations offer, the best performance and endurance and acceptable cost.
That's interesting. So if you put another SSD, so you are saying we won't get the same performance?
We don't focus much in terms of performance optimization for third-party vendors. We focus more on Intel. So for example, let me give you an example of performance optimization. So if you use Intel Optane SSD, it has an ultra-low.
Andre.
If you use Intel Optane SSD, it provides you with a low latency, like less than 10 microseconds. So CAS has been optimized in terms of I/O paths, to access the data as quickly as possible from that specific hardware. On the other hand, if you want to use QLC type of SSD, which prefers bigger I/O sizes, one of the optimizations that we are planning to introduce is to submit write I/O operations to the QLC device, so it yields better endurance and performance.
Just to comment again on your first question, some of these as well, like I think CAS has a lot more capabilities to actually tune the caching device in order to be a little bit more customized for your workload. So that's kind of a high-level overview of the classifications, the I/O classes that are output from OCF, and you can take those classifications and then make your caching device pull certain sizes so it kind of intelligently knows which data to pull from. Like in a lot of cases, the metadata will be of a smaller block size, and you can pull that out and cache it intelligently. Another one is kind of the tuning with flexible cache line sizes and things like that. And then another one is the ability to install and upgrade CAS. It's a much easier lift, especially the updates. Some of the other caching softwares, you had to do an upload and then a shutdown and do all these different things in order to get the cache functioning properly. But in a lot of cases, you can update and install cache on the fly, and it's much easier lift to actually get it implemented. So there's some other little features that just make it a little bit better. Yep.
So you mentioned that you also adding a feature for write-back caching.
Sorry?
So you're mentioning that you're adding feature for write-back caching. I would assume that requires spinning of threads or some sort of a thread context to do the flushes. So, so does the threading model followed by OCF follows the SPDK, like asynchronous non-blocking, or do you need dedicated threads?
Yeah, so the OCF itself doesn't make any assumptions about the threading model. And you're quite right in that historically, SPDK wasn't that suited to having a library spin up separate threads. But as it was shown on Ben Walker's presentation, the thread model is changing. One of the reasons was that we've seen multiple libraries like OCF and need to have a possibility to spin up separate thread. Right now, we're doing it a little bit different in the 1904 release, but we hope to enable the new threading model using OCF in the next releases as well.
Great, I think we're running out of time here. So if you have any more questions or want to talk about a specific application or workload, please visit our demo. We'll be manning that booth. But other than that, have a great conference, everybody, and thanks for coming out. Thank you.